What's up, guys? Alright, so we're going to do a Leetcode problem, and then I want to try and create some recipes for myself in preparation for going to live by myself, right? So I want to be able to create like a recipe archive that I can go back to and kind of get down a list of like ingredients to buy, right? That will be the idea. Ideally, I can have a list of recipes, and then, the list of recipes that I want to do for the week, I can probably buy collate the ingredients and, I don't know, have them for the week so that I don't need to go anywhere. Ooh, I didn't know you can just remove this like this. Sorry, I'm just picking out my mouse. It's all magnetic, I see. Not bad though, not bad. It's all magnetic, then I can like... Ooh. Yeah, I can just remove them. And I could just clean out the gunk. The dirty gunk. That is not bad at all, eh? Not bad at all. It just sticks together, damn. This mouse, man, is too satisfying. I gotta take this when I'm on my trip. Okay. Alright. So, we're gonna do a Leetcode problem. We're gonna also just do a monkey type. Alright, let's do this now. Okay. Not bad. Ooh, -1. One to 10. Funny how Minecraft opens up. Okay. Wait, G. Okay. Ooh. Wait, what's the mod symbol? Ooh, yeah, okay. I almost forgot about that. Zero, 2, 4, 6, 8. Predicate. Yield. Diraj, hello. What is this? Me typing. But now I'm not typing anymore. I'm gonna do a problem. Now here's the thing, I could do a graph problem, finish the graph section. Or I could work on dynamic programming problems. Definitely dynamic programming is important. And I've only ever done 4 dynamic programming problems, but maybe that is okay. I could finish off the try section by doing a try problem, or I could just continue with a graph problem. I might just continue with a graph problem. Number of connected components in an undirected graph. Number of connected components in an undirected graph. Epic. Okay. That means, let me open this up as the Leetcode problem. Oh, it's another subscribe to unlock problem. All right, so we're just solving it without Leetcode. It does mean though that, let's see, we've got to create number of connected components in an undirected graph. And this is this Leetcode problem. Okay. So there's an undirected graph with n nodes. Right, and there is also edges array where edges AB means there are edges between nodes A and B of the graph. The nodes are numbered from 0 to n-1. Return the total number of connected components in that graph. So given n equals 3, number of connected components. So a component, yeah, so there's 1 here. Oh, hello Zahype. Welcome, man. What happened to the haircut? What you mean, huh? What you mean? Connected components. So each of these are components, I guess. 4 to 5. Okay, yeah. Would it be best? Check 1. Go to the next. If you already know it's part of that graph. And then, meaning you don't process. So it's going to be, we're going to have a visited set here. My thinking is. Or you can have maybe, since it's undirected, nah, you can't make use of Kahn's algorithm. Okay, so in that case, I'm just going to say I know what to do here. I'm pretty sure. So let's create the adjacency list again, where our adjacency list is going to be initialized to an empty list for, yeah, in range of n. All right, then for each, so for n1, n2, in edges, adj of n1 dot append n2. Dot append n1. All right, so that's the adjacency list created. Now we're going to have a visited set. And in this visited set, I guess you could say for n, for node in range of n, if node in visited continue, else if it's not in visited, then you would either do a DFS or a BFS. We could do a DFS. All right, DFS of said node. And if, so then we would return visited, the length of visited, wait. Let me think this through. This visited will always be full. So it's probably better to do what? Jamil, how many Leetcode we at in this list? We are 89 questions in. This is our 90th problem. So not bad. And if we keep this up, we can definitely get all of Leetcode 150 done in during my internship if I do it every day. Should be good. Because if we're looking at, yeah, it's just 60 more questions. If I do one every day for 2 months, then we're good. But it'd mean that I have to do one every day for 2 months. Okay. Now the visited set here. Okay, I know. If visited is equal to, so length of visited, this is only possible on the first iteration. If it's only possible on the first iteration, why don't we just say if node is equal to 0, then you check if visited like maybe you don't need to do all this. Just say if it's not equal to visited after you do it from node equals 0, like if you do DFS of 0, and then you say visited, the length of visited is equal to n, you return this. Okay, but this is true or false, but we want to return the number of distinct, so that we need this. So if it's the number of distinct, we probably also need to keep track of a result. So Jamil, do you actually forget the problems you already solved with time? Have you tried going back to check? Well, actually, yesterday I went back to check on 2sum. And when I was doing 2sum, you know, I did forget like how to actually solve the problem, but I did remember that you had to use some hash table. I did remember you had to use target minus something. And when I was doing that problem, that's the only two things that I remember, which were the key points that I remembered, and I was able to solve it after a bit of struggle. But yeah, I think like me remembering that is only possible by me having written out you know, my key insights after each problem. And because, you know, the key insights for that problem was that target minus whatever, and using a hash table. If that makes sense. Okay, so we need a result. That means at the end of this, we're going to return a result. We probably get rid of this now. Let's see, so for node in range, yeah, so you're going to check for every node. If the node is already visited, then you don't do anything with this node, and you would continue to the next node. And then you would check. If it's not visited, then you would increment the result. And then you would DFS down that node. If node is this it? Imagine speedrunning Leetcode whole list 10 times. Oof. Yo, actually. If you mean like having done Leetcode so many times, you could just go through a speed run of all the problems, that would actually be pretty cool. That would actually be pretty intense. Not a bad idea though, hey. Not a bad idea. I feel like Leetcode himself could do his whole Leetcode 150 if he wanted to. You know what I mean? Yeah, that's it. Okay, so here's the thing, right? The result here, this should work as long as I've made the DFS correctly. Now, look, we can use DFS here, or we can use BFS, but we're going to use DFS. And so let's define DFS. Starting from a given node. Now, how this usually goes is a DFS of the children. So we're going to say n, or maybe yeah, okay, adjacent. So for n, I mean child points. How did I call this before? I'll just say n in. Oh, I'm gonna sneeze. No, it's not working. I've had hay fever. My eyes are actually really red. You can't tell because Or maybe you can. I don't know. Okay, adjacent of the current node. DFS. Node visited dot add node. And the children node, need to keep track of prev, current node, too much weed. No, it's actually hay fever, like full on. My pillow, I'm pretty sure yesterday my pillow was full of pollen. I woke up in the middle of the night and then was like, couldn't handle. I kept on, I remember like during the middle of the night, I was like rubbing my eyes. During my sleep, by the way. And then I wake up to it, my eyes are like red. I check in the mirror and then I go back to bed, but I switch a pillow out. So I use the one with less pollen on it. So I'm cooked, man. The only reason why the pillow was full of pollen was because I went out for a walk just yesterday. Then I had a nap for like 2 hours. And then during that walk, it was also windy. And during that wind, it must have gotten into my like face and head and hair. And then it's just like spread all over my, pillow. And then when I went to bed, maybe it's just worsened. Maybe the pollination went everywhere. I don't know. Okay. To me, this seems almost done. If prev is equal to n, then you would continue. Alright. Oh, one required positional argument, but none were given. I'm going to say none here. Not bad. Oh, wrong answer. Okay. I didn't expect that. Maximum recursion depth reached. Alright, give me a second. I think Leetcode did a live where he solved 50 problems off it in a day while learning Go. I see. Yeah. Nice. Interesting. Yeah, he'd definitely be mastered with all that stuff. Especially when the problem set is all his. And he's made countless videos on each of them. Okay, how is this a problem? Zero to one. Oh, right. We do know checks for if it's visited. Ooh, but if it's visited on the second round, is that a problem? It shouldn't be. If visited, so if n in visited continue. There we go. All right. Not bad. So that was pretty quick, I'm not gonna lie. Yeah, probably can't finish the whole list in a day, but I think it's safe to say more like 80 or more if you actually use the language you know and not talking to people. Yeah, that's what I'm thinking. That's what I'm thinking too. Yeah, if you're not talking to people, if you're probably doing it in the language you know, I think it makes sense, right? He's learning it in Go, which makes sense. You know, he wants to learn while also doing his own problems, so that's basically how he would go about that. Now with this problem though, like, am I thinking, is there anything else that I'm thinking from this problem that I could take as insight? Now, yeah, I could do a BFS version. So I want to make a BFS version of this just to practice my BFS, since we made the DFS pretty easy. So we're just going to do a BFS here. BFS of a given node. All right, so if we're, let's undo this. BFS of a given node. And we're gonna go to the front of this and comment this out. Okay, so let's try a BFS here. This is the DFS works, no problem. And you're given a node. Now, problem is, there's a way to set this up, and we got to be careful how we do so. You know that node is going to be the initial value in your queue, and you know that the queue that you create comes from collections DQ, and you're going to start with an empty list, or maybe you set the node in there, and then let's see, queue, while queue is not empty, queue dot pop left is going to equal to node. Okay, now node is what, yeah, you're going to do this if else statement. So for n in adj of node, if, I think you still need a prev node is equal to n. So node prev is gonna equal to none. Or yeah, none. Then continue if n in visited, continue, and DFS, BFS. I wonder if you can combine DFS and BFS. Of, now that's not how we do it, but we got to add it to the queue. Queue dot append the node and the current node. And then that would be it for the BFS, I believe. Actually, we don't ever add the node to the visited set. And so that's what we will do. All right, that should also work if done in a BFS manner. Yippee! Alright, so doing the BFS and the DFS, both pretty easy, I will say. Okay. I'm gonna copy all that. I know there's gonna be a duplicate. I solved this problem both in DFS and BFS, and it was a good extension to the problem that I did yesterday, which was, what's it called? Yeah, graph valid tree. Graph valid tree. So this is a graph problem. This is an adjacency list problem or data structure. Technically you can call it a hash table, right? But it's alright. Technically, like, the adjacency list was done using an array representation. Arrays or represent. I don't really have it. Okay. Well, we're gonna say arrays. Technically. Alright. I know I haven't added that to the other ones, but it's okay. I solved them both in how long? Roughly 15 minutes. And if that's the case, like, I might even move on to another one as well now. I guess there's not much insight to say about this. But look, you can do this in a depth first search manner. Oh, and you keep a visited. Oh, fuck. You keep a visited, not a visited set, but a visited array. That's an interesting way to go about it, for sure. But okay, that's alright. Yep. Alright, well, you can also use disjoint set union. You can also use disjoint set union in this problem. Okay, let's have a look here. If there's any new information that I can gather from this.
Welcome back, and let's.
Just gonna open it from YouTube. Let me think. Is there anything that I need to do before that? Yeah. I want to add this problem into Alacrity, into Leetcode. Now, number of connected components in an undirected graph. What number is this? $323. All right, 323. Number of connected components in an undirected graph dot pi. Count components, BFS. Yep. Git add dot git push. No, I mean git commit. One thing. Okay. Solved problem in around 15 minutes. Git push. So how many courses you have to take in your master's path? I think you said you won't do a final research path. So I might do a final research path, but it is a, how many courses? It is 4 courses, 3, so 12 subjects in total for the entire course. I think it actually comes down to around 10 if I'm taking courses that are double the points. So it's 10 to 12 in reality. And actually, I think it's more like 10 to 11 for my situation. Do you have Leetcode Pro? No, I don't. I don't think it's necessary for me. It's almost same here. It's 13 courses. Yeah, I see. Okay. Let's have a look at this problem.
Let's write some more neat code today. So today let's solve number of connected components in an undirected graph. And yes, this is once again a problem from
Union
our
find
75 list. The link to this spreadsheet will be in the description. If you want to take a look, you can see about 18 people are
Yeah, he does. Put the solutions for free. That's it.
So this is a problem, problem 34 from that list, number of connected components. So this is the graph one we'll be solving today. Probably tomorrow I'll finally go ahead and do Alien Dictionary. So the main reason I've been putting off Alien Dictionary and even this problem is because I couldn't really find a free version of these problems on the website Leetcode. So I actually went ahead and shelled out the $35 for a Leetcode monthly premium subscription. So for the next 30 days, I will have Leetcode Premium. So if you have any premium problems that you want to suggest, feel free to do that in the description. Big shout out to my Patreon supporters for making this possible. But yeah, so now let's actually get into the problems. So we're given a graph of n nodes, pretty simple so far. So the number of nodes will be given to us with an integer n, and we're also just given an array of edges belonging to this graph. Every edge is undirected. It connects two nodes A and B together. And all we need to do is just return the number of connected components in the graph. Now, what is a connected component? You probably already know, but it's basically just an individual portion of the graph that's all contiguous. See how everything in this portion is connected? We also have a second portion, which is disjoint, right? So these two components are disjoint, right? They are not connected to each other, but each of them separately is connected, right? Like every of these 3 nodes is connected together. These 2 nodes are connected together. Therefore, we have 2 different contiguous components. So there's not a lot of edge cases with this problem. It's pretty straightforward. So for example, if we were just given 2 nodes, 0, 2, no.
If he talks about union find in this problem, then perfect. I can learn about union find.
2 connected components, right? One node by itself does count as a connected component. And of course, if we're not given any nodes, n equals 0, then we return 0. But clearly, this is pretty straightforward so far. So there's a couple of ways to solve this problem. So we're given the edges as a list of edges, but we could make an adjacency list, which would make it easy to do a DFS search on the entire graph. So that's one way to solve this problem. Just go through every single node starting at 0, right? So we start at 0, then do a DFS search from here. So we're going to mark 0 as visited. We're going to see, okay, we can reach a 1, mark that as visited. From the 1, we can reach a 2, mark that as visited. So far, we've only done one DFS search, right? So therefore, we found one connected component. Now we are then going to try to do a DFS starting from 1, right? But what we're going to find is that's already been visited. So we don't want to add that to the number of connected components, right? So far, we still only have one connected component. We can do the same exact thing for second node. For node number 2, it's already been visited. No need to increment the number of connected components.
Yep.
Then we're going to get to node 3. This one has not been visited. Therefore, now we have 2 connected components. So now let's just do a DFS on here to mark all of them visited. 3 is visited. It has one neighbor 4. 4 is visited. And then there's none left. So we got 2 connected components. We'll try to do a DFS from 4, but it's already been visited. So therefore, we, in the end, notice we only had 2 connected components. Now, this isn't a bad algorithm at all. The overall time complexity is basically going to be, big O of E plus V, because notice we are going to have to
Oh
go
yeah, I
through every
totally
single
forgot
edge
about actually
when we
saying what
traverse the graph,
complexity
and
this
when we
is.
actually build the adjacency list, and we're also going to have to go through every node, iterating through it as we traverse the graph and as we, try to do a DFS starting at every single position. So this is going to be the overall time complexity. Not bad at all. But there actually happens to be a more natural way to solve this problem, and if you have heard of the algorithm called union find, it's a pretty rare algorithm to use in Leetcode, but if you do know this algorithm, then you basically know that this algorithm was literally made for a problem like this, literally made to be able to count connected components, as well as to be able to identify, disjoint sets and all that stuff. So I'm going to use this problem as an opportunity to go over union find once again. I think I've done this once before in a previous problem, but let's dive into this. So we're going to mainly be maintaining 2 arrays, one called the parent array, and we're going to have a value in that array for each node that we're given in the input. And initially, the array is just going to look like this, 0, 1, 2, 3, 4. So each index, so the index 0 represents the 0 node, index 1 represents the 1 node, and the value in every single array clearly matches that of every single node initially, at least. So initially they do match. What that basically means is each node is the parent of itself. So the way union find works, it's basically a forest of trees. So we're going to have multiple trees. Initially, clearly we have n trees, one for every single node in the input. And as we go through every single edge, such as 0 and 1, what we're going to do is take, okay, let's say 0 is going to be the parent, so 0 is a parent of itself, but what we're going to do to 1 is say, no, 1's parent now is going to be 0. Basically, what we're doing is just connecting the 2 nodes, right? And since we know that we just made a single connection, what we can say now is that, okay, we started out with 5 different connected components. We just merged 2 of them. Every time we perform a merge, we're basically taking the number of connected components we have, decrementing it by 1. So that's how we can keep track of the connected components. And there's one slight it's non-required, but it's an optimization that's pretty easy to make for this problem. We're going to maintain the rank of every single component. So basically for every single node, we're going to maintain what's the size of it. Basically, if this is the parent, what's the size of its entire connected component? Right now, what we would initially for each of them, it's obviously going to be 1, right? The size for all of them is going to be 1 initially, but since we just made this merge, we're going to leave the rank of 1 as it is because it's not the parent. But for the parent 0, we can say, okay, its rank is now not 1,
2.
It's actually going to be 2. Really, we're just talking about the size if this was the parent, which it is the parent, right? So what in our rank array, we could change the first 1 into a 2. And the reason we're maintaining this rank is basically just an optimization. So right now, you can clearly see we have one component of size 2 and we have one component of size 1. If we were merging these 2, right, would we want to merge this one as a child of this one? If we did that, we would get something like this, right? We'd get 1 and then 0, right? We'd get basically a linked list. So why would we do that when we would rather merge the smaller connected component underneath the bigger one? So if we
I totally forgot about
we'll
this.
get something like this, right? And clearly here
Okay,
you can
fair
see
enough.
if this was
That's
a tree,
epic.
the height of the tree is now minimized. Before we had a tree that was basically a linked list.
So Jamil, honestly, I think 1 to 2 problems with deep understanding daily might be better than rushing it in a few weeks, because you're probably just going to keep skipping to watch the vid for solution at that point and not try. Yeah, exactly. If you have deep, that's why I try to have deep understanding of the problems and just do 1 or 2 a day, with the idea that in a year's time it'll be all helpful when I'm looking for jobs.
Now we have a tree that's actually kind of a binary tree if you adjust your head by 90 degrees.
And it's more fun to take the longer path.
But so that's the main algorithm. So far we've
I don't
just
like
done
the stress
first
of
edge. So now let's look at the
deadlines.
second edge in our input, 1
could
and
say.
2. So we're connecting 1 and 2. And the way we're going to merge these is first we're going to get the root parent of both of these. So for 2,
Dang,
2
union
itself
find, man.
is its parent, but for 1, 1 has another parent, 0. So when you get the root parent of 2 nodes, that's how you know if they're already connected or not. Because if maybe this 2 was connected to 1, then we would say, okay, 2's parent is 1, 1's parent is 0, and then what we would say is, okay, 1 and 0 both have the same root parent, so therefore they're already merged, so we don't need to merge them again. But in this case, you can see 2 has its own 2 is the parent of itself, 1 has a root parent of 0, so therefore they're not connected, so we can connect them together. We can union these 2 components together. So this one is larger, this one is smaller. So we're going to add this as a child of 0.
Hold on, so that explanation I need to get back on. Isn't this related to path compression or something? Wow, long time, even its time complexity was weirdly notated. Yeah. Yeah, no, you're right. So this is kind of like path compression when you include a rank into the situation. You definitely bring up good terms here.
Binary tree, if you adjust your head by 90 degrees, you can kind of see what I'm talking about. But so that's the main algorithm. So far we've just done the first edge. So now let's look at the second edge in our input, 1 and 2. So we're connecting 1 and 2. And the way we're going to merge these is first we're going to get the root parent of both of these. So
you should have mentioned path compression though, right? I feel like
its parent, but for 1 has another parent, 0. So when you get the root parent of 2 nodes, that's how you know if they're already connected or not.
Oh, right.
Because
yeah.
If maybe this 2
that's the key point.
1, then we would say, okay, 2's parent is 1, 1's parent is 0, and then what we would say is, okay, 1 and 0 both have the same root parent, so therefore they're already merged, so we don't need to merge them again. But in this case, you can see 2 has its own 2 is the parent of itself, 1 has a root parent of 0, so therefore they're not connected, so we can connect them together. We can union these 2 components together. So this one is larger, this one is smaller. So we're going to add this as a child of 0. We're always adding to the root parent, right? We're not going to add it to 1, we're going to add it to 0, even though this edge is connecting these 2 together. When we add that edge itself, we're going to make sure that 2 is connected to the root parent because we want to minimize the height of the tree. And once we do that, we know that the rank of this is actually going to increase. So in our rank array, we're going to get rid of 2, and now it's actually going to be 3. And also what I didn't update in the first go around was the parent of 1 and 2. So 1 and 2 have new parents now. They both have parents of 0, 0. So this array is what we're going to use to go through every node and find its root parent. So we've done both of the first edges. Now the last and third edge, we're connecting 3 and 4 together. So in this case, it doesn't really matter which one is the parent. I'm just going to draw it like this because it's easier. So 3 will be the parent of 4. So for node 3, we will update its rank. Its rank is going to be 2. And the parent of 3 is going to stay the same, but the parent of 4 is now going to be 3. So that's just kind of the bookkeeping we're going to be doing to update our parent and rank arrays. But each time we made a union operation, we were taking our initial number of components, 5, decrementing it by 1, and so we did a union 3 different times, so we got a result of 2. 2 is the number of connected components we have at the end. But let's say we just had one more edge. Let's say we had...
why did he use that? Okay, hold on. I suggest you implement it. I did implement this problem, I think last year with disjoint, just to be confident because I wasn't back then. But I'm so bad at Leetcode, so haha. Okay, yeah, no, I'm definitely going to try this because, yeah, I mean, now understanding this problem, I can definitely see what data structures you need. So definitely going to do this after this.
And rank arrays. But each time we made a union operation, we were taking our initial number of components, 5, decrementing it by 1, and so we did a union 3 different times, so we got a result of 2. 2 is the number of connected components we have at the end. But let's say we just had one more edge. Let's say we had an edge 0, 2. So let's say we're trying to merge 0 and 2, right? first we'll get the parent of 2, the root parent, which is 0. Then we'll get the root parent of 0. 0 is the root parent of 0. So what we're going to find, since both of these have the exact same root parent, that means they're already connected. So we had 2 connected components. We're not going to decrement this by 1 because we didn't end up decreasing the number of connected components. We didn't even do a union operation. So in that case, we would return before we made any changes to the graph. Once we see that they both have the same parent, we return immediately. So that's the main idea of this algorithm. Once you've implemented it, you've written it out and coded it once or twice or 3 times, it gets pretty straightforward because most union find problems are pretty similar. So now let's get into the code.
Okay.
Like I said, this is a Leetcode premium.
Here's what I'm going to do, right? I'm going to solve this problem now by resetting my workspace and doing union find. However, I did notice that in the solution they did use a class of some sort, but I'll see when I'll need to use that, if at all. Okay, so basically union find has 2 operations, union and find. However, how we are going to implement this is a different story. We need to keep track of a rank, which is initialized to 0 times the number of nodes there are. We have a parent array, which includes, let's see, I for I in range of n, which means that you have 0, 1, 2, 3, 4, and that'll be it. So these rank and parent should now be equal. The union, look, I'm going to define a union and I'm going to define a find. Right, I'm defining a union of some kind and defining a find of some kind, where the union should return something and find should return something. Find, I think, should just return, in this case, the root node. And after you've gotten these 2 operations, what do we want to do? For n in, let's see, for node in range of n, node, let's see, node, okay, so union, I guess find of some node should give you the root. If the root is equal to, I don't think that gives me any concrete anything, but something union node. That's union node and the root. That's what I'm thinking. Now the union would then be, if you're given the node you want to union and the root, actually, should I say that is correct? Can you actually do that? Parent is equal to, so parent of node is equal to root, and the rank of node is equal to, is incremented by 1. So is the ranks always actually, they always start with 1s, right? So make that changed. And just return here, I guess. Ibrahim, hello. Nice of you to join. And find is where you have where you have to find the root of said node, and you would return this root. Do you know Nuru-us? No, I don't. I don't think I want to. You know that, I don't know if it was you, but there was a guy that someone recommended to look into, who had this startup and now he's under fire for some stuff, like security concerns of his app. And I forgot his name, this guy's name, but he was that e-commerce guy, or fast ship or whatever. I think you know what I mean though. Find of a node. So when you find a node, like what do? The parent parent, so this should just be itself in the beginning. The edge of concern, so the edge of concern is 1 and 2, say. Okay. Okay. So my thinking is, instead of this, it's going to be for node 1 and node 2 in edges. Find n1 and 2. So you're given n1 and n2, maybe. Find their common roots. That's what I'm thinking. But it might not be entirely the way. Yeah, Mark Liu. Yeah, Mark Liu, that's him. I definitely think I'm missing the ballpark here. I'm missing the mark here in some respect. Well, you know that these edges are going to be, I guess you might be finding this, and then, so this is root 1, root 2 maybe, of find of n2. And if these two roots are equal, or if they're not equal, then you union. Not equal. If they're not equal, then you union. Am I thinking of this right? And because after you've done all that, really, like, what's the main objective? It is to know the result of the number of unions. So however many number of unions you do, each union you do, you add 1? Is that right? Union 1, union again, union again. I gotta consider, say, when you do more and more unions, that's the number that you want to keep track of, right? Num unions is, I'm guessing, what we want to keep track of. Alright, let me think. And then the idea is we might want to just return n minus num unions. But let me consider this again, if there's anything that I need to consider else. So, number of unions, when you have 3 nodes, they're all separated. When you union one of them, you have 2 nodes. Union 2 nodes, you get 1 node. I mean 1 collection. So that makes sense in a 3 node case. But say in a 5 node case, union 1, you get 4 nodes. Union 2, you get 3 nodes. Union 3, you get 2 nodes or trees. And union 4, you get 1 remaining. So in a case of 5, yeah, it is. Every time you union 1, then that you kind of minus 1 of the trees. Okay. I can understand that. Okay, so I am convinced. However, how do you make the find and the union algorithms? Okay. You want to union n1 and n2. I think that's what you want to do. And you want to find the root, which in this case is just the parent node. Zahib, you built ship fast so that you can ship your apps in months, not weeks. Yeah, with security issues overloaded. That's the funny thing about him, man. It's look, that's why I don't follow these types of creators or types of people, and I am more of the type to take things slow and make sure it's done right. So I can't help but look at him and just look in disdain. Yeah. His sales were like 100 plus K. Yeah. Well, that's the thing, you know. I mean, you can market it really well. Like, he definitely did market it really well. At the expense of his credibility. So I don't think now in future he's going to be very much more credible. At least to the wiser people of the world. Yeah, regardless, I am kind of almost good here, but here, the union these are of two nodes. All right, so node 1 and node 2, I believe. The parent, we got to find the root. So the root of, say, 1 is equal to the parent node, parent 1. And ooh, let me think about this. Let me think about this. There's definitely something I'm missing here still. You kind of only found the parent, right? So if you've only found the parent, yeah, it's not necessarily pointing to the root node, but it's pointing to the parent. The root node, okay, yeah, so that means my find algorithm here is actually subpar. So, so while node does not equal to parent node, node is equal to parent of node. Yeah. Is that right? Until you find the root. So then you would return node. Okay. Cool, so this should be the find algorithm. Now the union operation of n1 and n2 if they're edges, then it means that they will have a root together, right? If they're already union, then you don't need to worry about it. So maybe it's just a matter of keeping track of the number of unions that you do which succeed, that is. Alright, so if that's the case, maybe, you know, this is fine. If R1 does not equal to R2, num unions plus equals 1, equals 0 originally, okay, and then this is where we actually do the union, where the parent node, we haven't used rank yet here at all. Would you take whichever has the higher rank? Like, that seems like the logical step. Okay. Cannot access local variables, so this is just going to mean that num unions, non-local, num unions. Node is not defined. Alright, give me a sec. Do you recommend any courses for DSA? I'm terrible at this. Honestly, just I don't really have a recommendation of a DSA course, but I would just use Geeks for Geeks or W3 Schools as your material. But like if you're trying to, you know, aim for Leetcode practice and prepare for technical interviews, do Leetcode, and then the DSA you come across, learn that DSA while you're doing the Leetcode problem. That's my best approach. Okay, but where is this? Why is this happening? Okay. Parent of, node 1 or node 2. Shoot. How do I even think about this? Oh, it's a hype. No, I read it. Yeah, I mean, still like, I mean, we don't really need to talk about ship fast anymore, but it's literally like just security issues on security issues. Node, nah man, I'm not doing this right. Let me think. So node equal to node 2. And rank is equal to rank 1. Sorry, root. Else node is equal to n1 and root is equal to root 2. All right, we're gonna have to see. Oh shit, that's actually passing? Okay, not all of it. Okay, but it passed for the first two. I didn't expect both of those to pass. Since there's a fact on how to learn DSA, might as well add it to your suggested rec in the description. Honestly, yeah. I probably should. Okay, well, we've had an attempt. All right, we're just gonna have a check now at what our solution could have been. So DSU is disjoint set union. So the rank and a list of range. Okay, sure. Right. I mean, that's fair enough. Find the current node. If current does not equal to the parent current, then parent current is equal to the parent of the parent current. And then current is equal to self.parent current. Interesting. So along your way of finding, you update the root parent. Interesting. So how would that look like for me? That would look like the parent of the node Ooh. Oh, shit. Okay, that's a little mind-boggling, but let's see the rest here. So the union operation has find u, find v, or in my case, it's root 1, root 2. If this does equal, then you return false. Right, yeah, for sure, you can do it that way, right? And else, so if it's not the same, then if a rank is greater than the other rank, then you would say pu is equal to whoa. You just switch them. Yes, you can. And then you change the root. Oh. So you don't even need to keep track of node. Right, okay. Interesting. And then, oh, you just decrement the result. Oh my god. Okay, so look, I am doing this almost correctly. I believe that if I just change, say, the node here, change this to... oops, undo. So R1, R2 is equal to R2, R1. Then R1, R2, R1. Parent of R2 is R1. So parent of R1. It really doesn't matter which way is which. Oh, but I think I'm going to be... let me see, which way is which? So you're only going to add it to R1. Num unions. Num unions. Find. The find algorithm, though, doesn't matter. No, it doesn't. It just means you're shortening it. Okay. The find part of it, you're just shortening, so it doesn't matter too much. But this union part, I think, is the main concern. So if R1 does not equal to R2, then if rank of R1 is greater than R2, then you want to add it to R1. If you want to add it to R1, wait. You want to add it to R1. Otherwise, you want to add it to R2. All right, let's see. All right, that's good. All right, we only had to, we were pretty close. We were pretty close on our way. The extra optimization that you do with the union, with the find in the union find, is this, I guess, extra step of removing the number of find operations you have to, or node iterations you have to do within find. Which, which I can make sense of, which does make sense. Because if you think about this like a pure function, it makes sense. So I'm going to say, right, that we solve this problem using our method, which is pretty close. But there are a few optimizations that you can do here as well. So using disjoint set union, we can get a solution that is time complexity O of V plus E times some alpha V. So it's some function of V which is interesting. I gotta understand that. Where alpha is used for amortized complexity. Interesting. Space complexity is O of V. Ooh. That does make sense. It is O of V. Ooh. But amortized complexity is the difference, is what's different from this. What is amortized complexity? Amortized analysis is a method of analyzing a given algorithm's complexity or how much of a resource, especially time or memory, it takes to execute. The motivation for amortized analysis is that looking at the worst case runtime can be too pessimistic. Okay, so what amortized is like an average? I need a good definition of amortized analysis. Interesting. I guess you can highlight this. Amortized complexity. Okay. Code. Whoops, not code. Alacrity. I gotta quit this. Quit. Okay, cd Leetcode again. We're gonna go into nvm. Sorry. We're gonna, let's see. YYD, sorry, GGDG P undo. Control V. Git add, git commit. Solve. Okay, solve using union find, where solve using union find on so I solved this problem with only a single line change. A single function change in the union algorithm for the rest to function as required. Git push. Okay. Now the other thing with this DSU is, let's see. The other thing with this DSU is in the find function, you could optimize the function so that future calls get updated to the newer root. In which case, we're going to have optimization. And this new line is so it turns out to be pair node is equal to pair node. Is that right? Yeah. Very cool. Very, very cool. So if I add this here now, that would be the optimization that was required to solve this problem, I think. Yippee! Alright, that optimization still works. That's good. If I actually made this greater than, is that going to make a difference? It will, right? It doesn't. It just doesn't make a difference. Alright. I guess it doesn't make a difference because, you know, we're not really targeting that specific issue. But okay. That is still exactly what I'm thinking about. Good, very good. I like this so far. Yeah, I could make this a little better looking, arguably, but this is not bad already. You know, I could instead do this and then make this as return, right? And then make this as one indentation less, and then keep this as is. Num unions. Now here's the thing, the num unions is cool. You could return false and you could return true. Making no use of num unions at all anymore. That would be one way. But does that matter to me, you know? Doesn't matter to me, I don't think so. If that union was done or if it wasn't done. Man, it would look better if I did it the right way without using non-local. But I'll stick true to what fuck it. I'll just stick true to what I already have here. And I'll just copy this over again one last time. So we're going back to Alacrity and redoing that problem. Oh, undo. GG, D, DG, P, undo, Control C, paste. I think that's fine. Right, quit, git add, git commit, I guess chore, refactor, make prettier, right quit all, git add dot, oh wait, git push, git exit. Alright, all good. Yo, what's up? Or as you Australians say, g'day mate. Yeah, that's what we say. G'day. Alright, so we're happy with that problem now. I'm happy with that problem. You know, I took a lot of time just to fully understand it. At least the union find aspect. Now that means though that I could go back to the previous problem, graph valid tree, and perhaps do this in a union find approach as well. And yeah, it could work. Could very well work. However, do I want to do that? Do I want to do that right now? Could I? Could I not? Do it tomorrow, maybe? I could do it tomorrow. Maybe I'll do it tomorrow. Because what I want to look up right now is do a little bit of research on wait, let me cross off now this off my list. I want to do a little bit of research on a recipe manager. So recipe manager, self-hosted. All right. Tandoor. Mealy. Dev here for kitchen has a way to export recipes, field and I can look into the feasible build and port for Tandoor. Mobile app. So mealy or grossy might be more than you need, but as a recipe manager included. Okay. So mealy seems like something. We got awesome hub, which gives me different alternatives. Can you add videos to Obsidian Notes? You can embed videos. I think you can like actually upload, you know, you can put a video into your workspace as well and embed it that way as well. But that'd be a lot of, you know, data consumed up that I personally wouldn't, you know. Okay, recipe management, recipes, recipe Sage, Open Eats, and Mealy. Interesting that recipe Sage is something Give me a sec. I want to wear a jacket. Be right back. Looks kind of cool. Add to shopping list, I see. Right. It is like very, what's it called? Material UI? It is very material UI based. I suppose this is probably also very UI based. Let's see. Yeah, it's all very material UI based. What's this? Oh, you just tick it off, I see. Is there a way to say I mean, this actually feels like it has less features than meal sage or recipe sage. Complicated. Mealy, okay, well, still they suggest mealy. Meal planner, auto backups, import recipes. Maybe that's alright. Ah, they do have a shopping list. Fuck it, we're just gonna use mealy. Mealy's gonna be good. What the heck? Potential security warning. Okay. Okay, well, mealy looks like this will work. Base URL. Man, alright, merely is going to work if I did this on TrueNAS. However, like, what are the backup considerations required for this? Because I haven't considered that. But anyway, if we use this, I could definitely get started. I guess how to back up TrueNAS scale Kubernetes. Or storage configuration. How to back up TrueNAS scale apps, probably, right? So Zahib, do you think there is a difference between DSA and logic building for one who is learning, let's say web dev? I would say there's no need to be a difference. Like foundationally, if it's, if you think about things logically, then I think you're fine. But say at a higher level, if you're talking about, say, learning web dev, a lot of the process, the logical decision is to, if you run across an error, search what it is on the web. That's the logical next move. And then if it's for DSA, the logical move for that is to actually search on the web and learn about not the error, not any error, but the specific concept. And for me, they're just two ways of saying the same thing, of kind of know what your next step is logically. I don't know if that makes sense. Hello, Dinesh. Welcome, man. Yeah, as a hype, that's it. Dinesh, what course am I doing right now? Well, I am done with my exams, so I'm not thinking about any courses at the moment. However, I'm trying to set up a self-hosted recipe manager at the moment, because I'll be making my own recipes at some point when I move away. And I should start just like making my own food. Like, I've been living at this house for 20 years, 22 years. So, bro's gotta cook for himself at some point. That's not a very good solution there. Dinesh, so you're doing engineering CS. Is that still software engineering? Is that still considered software engineering? Or is this also like more broad engineering? I don't know if that's possible. Heavy script backs that all up locally, retains decent limits. Would be really useful as a mechanism of exporting in a common format the container configuration. Up towards the top right, rogue button in Jira. I think it's a matter of me having a go. True tool. Heavy script. Don't bother, upgrade and use the Docker container implementation. I'm still not convinced how this is at all backups and restoring. For any possible disaster regarding my TrueNAS scale, I would like to recommend app or method to effectively allow the backing up of all the installed apps and configurations to allow for easy restore should something go wrong in the future. I don't use Scale nor the apps, but I imagine you could just use ZFS snapshots and ZFS send receive to your backup target. Of course, this requires another TrueNAS machine. Alternatively, you could probably use rsync, but that definitely won't be nice as ZFS snapshots. Thanks for the reply. Unfortunately, I do not have another TrueNAS system. I will look through the app repository, but last time I looked, I couldn't identify an app that has a simple backup and restore feature for apps and their associated configs. Doesn't downloading the config to your PC also include the apps and their setup? That's not necessarily. I've never played with it, but TrueNAS has Velero native backup solution. HeptioArch. HeptioArch was such. That's a weird name, eh? The words start looking like Russian for me after hour 6 of trying to learn through reading documentation. Do you mean just like generally reading through documentation? For sure. I mean, at hour 6, I would probably too. I'm a full stack web dev Mern. Any suggestion not getting internships? Right, so I mean, even if you're a full stack dev, web dev, it depends on what internships you're looking for, really. But knowing your Leetcode would be good as a number one step. Maybe like 30 problems solved. You can get a front-end job pretty easy, or not pretty easy, but you'd be able to pass the Leetcode aspect of it. You need to have good behaviorals. That means following the star framework and all that good stuff. But yeah. So Nahi, yeah, I'm trying not to rely on YouTube vids, but after a while, the words start to not make sense. Yeah. That's fair enough. Maybe at that point you just need a break. You know what I mean? I would give myself a break. So heavy script by True Charts. Maybe I've got to look into heavy script because I guess that's what everyone's using, it seems. How come it got archived? Archive repository notice due to the upcoming update. Ooh. They will just be replacing it. Wait, what? So they're getting rid of K3s to replace it for Docker Compose. Yo. That is interesting. Because for one, I wanted to learn more about K3s, but if we're getting TrueNAS to a point where it's just going to use Docker Compose, firstly, that'll be good, but also bad in the sense that I won't be able to learn about K3s as much, or, you know, Kubernetes as much, but it would also mean it'd be easier to manage Docker containers using Docker Compose. Nah, yeah, I see what you mean. Well, I guess you can join my streams to stay in faux productivity, or at least get some idea of how I'm thinking. Okay. So to me, at least, this seems like a very under evaluated solution. To me, if everything's moving to Docker Compose, I might as well just use Docker Compose for Mealy as well. Which means maybe I won't even use TrueNAS at all here. If that's the case, then we might just close up TrueNAS and just use Mealy. We'll go to Mealy. Okay, let's check out the getting started guide of the introduction. Okay. Honestly, I will join the Discord for Mealy. Mealy's Discord. Azula? Yes, I do. I do have Home Lab set up. So mealy.dev. I'm gonna probably put it under image because image is pretty cool. Way cooler. Go to live now. Get rid of that. Okay. Meaning now I can go back. Oh, Azula, you're working on getting stuff to start your own, I see. Not bad, not bad. You got any ideas? Is this built using Fast API? Nextcloud cookbook, I see. Tandoor recipes. Not bad, eh? Easy setup with Docker, localized for many languages. Okay.
Huh?
None yet. It'll be nothing crazy since I'm going to be my first time doing it. Yeah, fair enough. If anything, I suggest like a Raspberry Pi, you know, because that's what I started off with. Let's see. It's 12 o'clock now. Ooh. Damn. Okay, actually, you know what? I gotta get ready for something else later. I gotta go to the gym first, so I will do that now. And I might just call the stream a day today. Because I gotta eat lunch and then, yeah, there's a meetup that I have to go to. Alright. Regardless, we did a lot of study on Union Find today, and we did just a little bit of sussing around for the Mealy, which is the next app which I will self-host. Okay, that's it. Thanks guys, thanks for joining, and I'll catch you guys maybe tomorrow, but hopefully within the week. All right, peace.